today we are going to continue with what we have done in the finding state space representation for given transfer function. So far, we have, taken one approach in which we said, if you have transfer function, I can get what we call state variable canonical form, where the A matrix will be, it has 0 everywhere except the super diagonal, and the last row, it has the coefficient of the denominator of transfer function in reverse order. Today, we are going to have another type of representation, another canonical form, we call it. These canonical forms, they have different applications. It depends on the application, you will, find your state space representation. So suppose I have, this is again, nth order system, nth order transfer function, and I would like to obtain the state space representation. That basically I want to obtain x dot equal ax plus bu, y equal to cx plus du. The A, B, C, and D matrices, which we are going to obtain, they have different structure from what we have taken so far. However, we will see they are related. I mean, I can go between the one which we are going to derive and the phase variable canonical form. They are related, and we can get one. If you have one, you can get the other. So let's proceed in here. What we want to do in here, let me cross multiply. Okay. So simply just cross multiply. Multiply the y by this one and u by the numerator. Any question here? Now, try to move everything to one side and try to collect the coefficient associated with the power of the polynomial. That's basically, let me write it as Sn y of s, Sn minus 1. And what is associated with Sn minus 1? An minus 1 and Bn minus 1, where An minus 1 multiplied by y, Bn minus 1 multiplied by u. So I'm just, collecting terms associated with the various order of the polynomial. Any question here? Now, let me divide by let me solve for y. I'm solving for y. Y of n, y, basically you take everything to the other side, you take everything in here to the other side and divide by Sn. So Sn minus 1 divide by Sn will give you what?
1 over s.
1 over s. Okay?
Clear, doctor.
Okay. Now, rather than, what I want to do, I want to construct the signal flow graph for the system. But rather than, working with the nth order, let me take the third order, let's understand the procedure, and then you go to the
general form
dimensional system. That's basically, suppose I have a third order system. It's exactly what we have before. Rather than going to the nth order, let's take third order. Okay? I'm doing it in this systematic way because I want certain particular representation. Now, how many integrator I have in here?
Well, it appears that we have 1 over s, this is an integrator, right?
Yes.
Then we have then 1 over s squared, it's 1 over s multiplied by 1 over s, so it's 2 integrators together, right? So 1, 2, 3, 3, 6 integrators.
No, come on. We have only 3. We can, I mean, we can use only 3. Yes, you are, well, I mean, if you take each term, the...
Exactly, yes.
Yes, you are
Because
right.
I didn't know, Doctor, what is the idea behind that.
Okay. In here, I have 3 integrators. Let's say, suppose I want to go between u and y. How many integrators I need?
3 integrators.
3 integrators. So, suppose this is u, the input. And suppose I have, this is 1 integrator. And this is another integrator. And a 3rd integrator. And suppose this is, let's say this is y. I can get y also in here by have a gain of 1, and this is y. I can, look, any node, I can make it as an output node, but I cannot make it as an input node. Okay? Now, let's assume that A naught, B naught, A1, B1 equal to 0, all zeros. So how do I find y in terms of, I'm assuming B1, A1, B naught, A naught equal to 0.
So we start, Doctor. We have, for example, we will start, for example, with the first term here, minus A2 feedback, right?
So it's going to be from A
B2 here, B2.
U, okay, to the point before the integrator. This is B2. And minus.
This should be B1, Doctor, ولا؟
No, this is B2.
وانت تاخذها feed forward.
Yes,
تمام
yes.
تمام.
Okay, A2. So look, y equal to, the signal is coming from here, B2 times U minus A2 times Y, and the whole thing we multiplied by the integrator.
This is the idea of feed forward here.
That's exactly, this is, they call it input feed forward realization. Now, let me keep B0 and A0 equal to 0 and add to what I have the second term.
So you will get it to before 1 over S, the second 1 over S.
Exactly. So I will take from here.
This is B1.
This is going to be B1.
And then you take from Y, A1, minus A1.
Minus A1.
This is very systematic here.
And I have to, of course, multiply by 1.
All these gains by 1, Doctor, right?
The gain, if they're
between the integrators, 1.
If we put either the gain is known and I will put it on the branch, or if it's not, you know, we'll put 1. So this is 1. This is 1 over S. This is 1 over S.
I see.
Well, now let's take all of them together. So let me take from U to this point, the gain will be B naught, and from Y to this point, minus A naught. And again, let me put in here, connect 1. So this is my signal flow graph. This is the signal flow graph of the transfer function. Any question here, Shabab?
Clear.
No, Abdurrahman, let's give the other opportunity. Shabab, any question?
Yes, Doctor, it's clear.
ما شاء الله. Great. انتوا الثنائي ما شاء الله عليكم. Any other okay, now let me assign.
Here, each node here is just like a summing point, right?
Yes, each point, this is a summing point.
Okay.
They are summing point, yes. Now, assume the output of an integrator a state variable. So this is output, let me call it x3. This is output of an integrator, call it x2. And this is an output, call it x1. Okay. Now, if this is x3, what is before the integrator?
It's
X3
differentiated for
x3 dots. And this is going to be x2 dots. And this is x1 dots. Now, let me construct the state space. So what's x1 dot equal to? What's x1 dot equal to?
B0.
Okay, B0. Okay, minus A naught x3. Do you agree? This is x3.
Yes.
Yes.
Plus B naught U.
Yes, correct.
Okay, how about x2 dot?
We have minus A1Y
Okay,
plus B1U.
plus something else.
B1U.
No, it is this one in here. So it is going to be x1.
From X1, yes.
X1 plus
minus
A naught x3 plus
A1.
no, sorry, A1. A1 plus B1U. How about x3 dots?
Similarly, we can.
X2
X2.
plus B2 UFS.
Okay, minus A2x3 plus B2U. How about Y?
X3.
X3.
That's it.
Okay, now let me put it in a matrix format. So I will have
X dot X1 dot.
Any
X2
question?
dot. Yes.
So what's x1 dot? X1 dot, we said, minus A naught x3. So what's
0, 0 minus A3 minus A0.
so 0, 0 minus A naught
plus B node.
plus B naught. Okay, how about the second one?
Well, we have 1.
1,
0 minus A1 B1.
and B1.
And the last one.
0.
minus 1 minus A.
No, 1 minus A2. Okay. And B2. How about Y?
0, 0, 1, x3. 0, 0, 1, x1, x2, x3.
Exactly. So now look, what we have, the matrix A, it has again zeros And now not the super diagonal, it is the lower diagonal will be 1, and the last column will be the coefficient of the transfer function.
The coefficient of the denominator طبعا.
Or the denominator. The numerator, they are here.
Associated with the u, yeah.
Yes.
And why is that, Doctor?
Okay.
Why we don't have the ones in the super?
Because of the structure of the system. We will.
I see.
Okay, we will come to the diagonal as a matter of fact. So look.
But this we can now generalize this, Doctor, right?
Yes, for sure.
And you can take it from B0 to Bn minus 1 and A0 to An minus 1, and the lower diagonal will be 1, 1, 1, 1, 1, and so on and so forth. So
Exactly.
we have
Exactly.
an infinite matrix.
Doctor,
Yes. تفضل.
the example we solved last class, we can use the same method here.
The example. Did we take example last time?
Yes, but with another method.
Yes. Yes.
Okay.
Yes. As a matter of fact, look, we are going to have an example after shortly, which cover both.
Okay, thank you.
Another important point. Okay, let me first of all, this is third order. The nth order, this is your signal flow graph. Okay, this is exactly the same. And this is basically the nth order realization. As I said, the one in the lower diagonal, super diagonal, the last one, the last column will be, the last column is going to be the coefficient of the denominator. The B matrix represent the numerator, and this is your Y. Look, what we have said, even though those representation, the one which we take in before, which is we call the phase variable canonical form, and this one, they are different. However, they represent the same thing, same system, and they are equivalent. So if I have, a transfer function, and I already got the phase variable canonical form, I can relate it directly to this one. Okay. Remember, let's take 3 by 3, and it will be clear to you. Suppose I have the 3 by 3 for the phase variable, variable canonical. Okay, in there I have, suppose I have third order system, so x1 dot, x2 dot, x3 dot equal to 0, 1, 0, 0, 0, 1 minus, let's say, a0 minus a1 minus a2 x, which is x1, x2 plus 0, 0, 1 u, y equal to b0, b1 and b2 x. Let's take third order from here. Input feed forward. Feed forward. What do I have? I have x1 dot, x2 dot, x3 dot. This is equal to, 0, 0 minus a0, 1, 0 minus a1, 0, 1 minus a2, x, and I will have, b0, b1, b2, u, y equal to 0, 0, 1, x. Tell me, is there any relationship between those two representations? This is one representation, and this is the other one.
Is it the transpose, the A matrix?
Exactly. So let's say, let me call this as A feed forward, A input feed, IF, input feed forward, equal to A phase variable, okay, transpose. This is the A matrix. If I have this A matrix, I can get immediately transpose it and get this A matrix. Okay. How about the B of this system? Okay. B of input feed forward equal to what? Look at this one and what we have in here. It is C transpose of the phase variable. Transpose this one and consider it to be the B. How about the C of the input feed forward? This is equal to what? B transpose of the phase variable. Take the A, take the B in here, transpose it, you'll get the C. So they are related. Once you get one of them, you can get the other directly. Okay?
So
Yes.
for the A matrix, in which we have the super diagonal or the lower diagonal,
Yes.
in the case of canonical or case of phase one,
Yes.
and this. What is the advantage that we can have, or that we will have, in terms of computational advantage processing such matrix?
Look, as I said, if you go a little bit further, okay, and you want to check what we call the controllability of the system, the first one, once you have the first one, the system is always controllable. If you want to do state feedback, that basically in the feedback system, if you want to design a controller, one type of controller called, okay, state feedback controller, where you feed all your states back to the system with certain gain. It will be very simple if you have the system in first representation. Now, the other one, if you want to build what we call observer, the second one will be fit perfectly. The computation will be very simple. So maybe in here at this stage we don't appreciate what we are doing, but if we go further, unfortunately we don't have time to go further in the course in here. That will, that will give you, why they are moving in this method or the other method. Okay. We will be giving also one more method, which is the diagonal. Your A matrix will be a diagonal matrix. And that will be great. Okay. So, example. Abdurrahman, did I answer your question?
Yes, Doctor. More than you give us more than you need.
Okay.
Doctor,
Yes.
please can you go back? Yes. The phase representation and the feed forward representation, are they equivalent?
Are they what?
Equivalent?
Yeah, the two systems are equivalent. The two systems are equivalent. Equivalent in a sense, what does equivalent mean? If you want to, okay, one test for them. If I look into the eigenvalue of this matrix and the eigenvalue of this matrix, they are the same. They have the same eigenvalues. If you excite this system by an input, okay, with certain initial condition, you excite this system by input, but scale your initial condition to fit this one, you will get the same output. So
Doctor, finding the eigenvalues of such system, we will, if we stick to.
We'll come to it, Abdurrahman. We will come to it. By the end of this lecture or next lecture, we will come to how the eigenvalue of the system.
So, Doctor, here the system is the same, but the initial condition are different.
the transfer function is the same, but the state space look different.
Okay.
Okay.
Clear.
The transfer function, as I said, again, let me put those three models: differential equation, transfer function, state space. Okay. From here to here, not unique. While this is unique. Okay. So if this is unique, this is going to be unique. And there is, okay, the relationship between those two. So if you go from transfer function to state space, you will have infinitely many representations. But all of them, they are equivalent from input-output point of view. Okay?
Okay.
Other question?
Doctor, that's why we have phase and input feed representations, because they converting from transfer function to state space is not unique.
It's not unique.
Okay.
Okay, let's take an example. Look, this is an example. Suppose I have this example. The transfer function g of s equal to 4s cubed plus 25s squared plus 45s plus 34 over s cubed 6s squared plus 10s plus 8. And I want to get the two realization for the system. The phase variable canonical form and the feed for input feed forward for the same system. First of all, so far what we have done, we were addressing the issue when the denominator degree is greater than the numerator degree. Now in this case they are even, they are equal. So the system is just proper system. So how do I proceed?
Do long division.
Long division, or remember we need ax plus bu y x, sorry, cx plus du, this is y and this is x dots. The matrix D, this matrix, we can get it directly from here by taking, okay, D equal to limit s goes to infinity of g of s, which is exactly the same as the, you know, the constant when you do the log division. So what does
4. 4.
This is equal to 4. Now,
but this is, Doctor, not the value, not the final value, صح?
This is D, the D matrix.
I see.
This is the D matrix. You have A, B, C, and D. So far, we talked about A, we talked about B, we talked about the C. The D is the direct coupling from the input to the output. And
I see.
take it in this way or do long division. So if I have, this is my D, let me subtract it from the given one. And now I have, this is transfer function, the one which we already have done before. So now the realization.
Now it will become, Doctor, the same as before, right?
Exactly, exactly. And this is, as you said, you can memorize it. Okay.
-8, -10, -6, -1.
U, y equal to x plus 4u. So in here, what do I get? In the phase variable canonical form, what did we say?
0, 1, 0.
0, 1, 0.
0, 0, 1. -1, -6, -10.
Minus, what did you say?
-1.
Wait,
is it minus?
No.
Is
Minus
it? Is
8.
it?
You take this one.
Why, Doctor, you didn't use the input forward representation?
-8. Wait. -10.
The other way around. Maybe
Yeah.
you're right.
No, no, wait. No, this is not correct. No, there's one more thing. I said mine. Okay, wait. Yeah. Okay. Yes. And minus
Doctor,
6. Yes, minus 6. But is this yes?
yeah, yes, because we stop at n minus 1.
Exactly. And then we have 0, 0, 1. And the C matrix is going to be the numerator in reverse order. So 2, 5, and 1. And this is your system. This is in phase variable.
This is in phase variable. If we want to input forward, transpose everything, you transpose the A.
The other representation, this is phase variable.
But they are identical, Doctor. I mean, there is no kind
No,
of,
what do you mean identical?
not identical in the sense that they are the same, but identical in the sense of computationally.
But as I said, Abdurrahman, this is, okay, the application, where are you going to apply them?
I see.
The next step, which will make the difference between them. If you want to have what we call state feedback, if I have the system in this way, okay, all what I have to do, modify my, I can get the state feedback from the last row only. While if I have the other representation, no, I cannot do it. So the computational advantage will show in their application. If you go, unfortunately, as I said, there is a concept of controllability. Now this system, if you talk about the controllability, the system is controllable always in this format.
I see now, but will we, Doctor, investigate this more?
No, because the time, okay, we are only taking just the state space, part of it. Because we have to go and cover the, the stability in the S domain. Okay, so now the other representation, okay, x1 dot, x2 dot, x3 dot will be, okay, this is the feed forward, input feed forward. Input feed forward. Okay.
Transpose A.
Just 1 second. Okay, you transpose A.
Yes.
So what do you get?
You get basically
1,
yes,
0. The first
exactly, and then 1, 0, G.
0.
No, 1.
Just 1 second. This is okay. I'm transposing. This is going to be okay. Look, I'm transposing this one. This is what I'm getting. Now I'm transposing the second one. This is 1. Okay. And then transpose the last one.
-8, -10, -6.
-8, -10, -6. Yeah.
Minus 6. This is 10.
Yes.
X1, X2, X3. And this is going to be, okay.
And this time, yeah, we
I1,
from, yeah.
and this is 0, 0, 1. Okay. This is basically what I'm saying. This is the input feed forward 4.
This is not always controllable.
No, this is observable. The other one is controllable.
Doctor, if you can just elaborate more, what do you mean by observable and controllable?
Controllable system is that, okay, I can manage all of you. Okay, that basically, suppose you have a circuit. Okay, suppose you have a circuit. Okay, let's say this is a voltage source. And let's say I have a capacitor and yes, inductor. Okay, this is a capacitor. And let's say in here I have a resistor. And let's say I have, this is V out. This is a voltage source, capacitor, resistor, inductor, another resistor. And suppose there is a switch in the system starts operating. What will happen to the energy in the inductor after a certain time?
Now the capacitor, again, Doctor, the question, you run the circuit.
You run the circuit, okay, and you have
for a long time, the inductor will be short circuit.
Will be okay. There will be no energy. It will be nothing.
Yeah, there will be no drop on
Okay.
it because
Now, can you? This is the input volt. This is the input. Can you utilize V in controlling the final state of L?
Well, we can.
How? Tell me.
I need to think, but if we
no, don't think. No, don't think. No, tell me right away. Don't think. How? This is open circuit. There is nothing coming in here except.
Oh, open circuit. Yes, of course. I cannot.
Okay. This is by the input. I cannot control part of my system. We call this system is uncontrollable. Okay. The concept of observability, it is, from the output and the input, can you estimate your initial condition? Okay. So as I said, we are not going to go to that one. If you go there, you need this concept. You need them. Okay. Now, any other question? Is this clear, Abdurrahman? Is it clear what's controllable and observable?
Yes. So what I understand now, Doctor, is if the system is controllable, that means that I can control it by tuning the input.
Exactly. Finite time. Okay. This is as simple as that. Okay. Now let's take one more approach. Let me assume that I have a system, and suppose my the transfer function, I can factorize the denominator, and the factor I have simple poles. If you have repeated poles, we could modify this approach, but assume that we have the poles are not repeated. Simple. Okay. Now, let me do partial fraction. Can I do partial fraction in here?
Yes, you can do.
And this can do it anytime.
Okay, you can find C1, C2, and so on. Bn is the, because of degree they are the same, so it's going to be constant, and so on. So suppose, let me call this is, okay, if you multiply, if you multiply everything by u, okay, if you multiply everything by u, so this is going to be what? I'm going to have, this is B2u, this is u, and u, isn't it? So suppose I want to represent my system. This is the input. This is, let's say, Bn, okay, and let's say this is, let's say, okay, this is, let me call it Y1, Y2, until Yn. And how do I get my Y? from here. What do I do?
Parallel reduction. You add them all.
Parallel. This is y. Okay. The first one we said constant. Now, tell me, what is the realization of this system? This is, let's say, this is the first.
C1 over S plus, yeah.
So what is the realization? What is the order of the realization?
It's e to the power of minus b1, Dr. T.
No, not in time domain. No, state space.
It's one.
Which is, okay, so assume, okay, let me write it. Let me, okay, suppose y1, okay, equal to C1, okay, S plus P1 U. Let me go further, make it, because you know what okay, let me say y wiggle equal to 1 over S plus P1 U. So what is the state space for this one? X1 dot equal to what? What's x dot equal to?
Y.
Minus P, isn't it? Minus P1 plus X1 plus U. And Y equal to, if I want Y, it's going to be Y equals C, Y1 equal to C1, Y wiggle. So it's going to be C1, okay, X1. So, or basically, look, go to the approach which we have done in here, the general approach. Okay, I have only one order, first order. What does this matrix will look like? What does the system will look like? Tell me.
One will be one.
It's going to be minus, okay, it's going to be minus, let's say, AN or A1, A naught, because it's only one. Okay, this is minus A naught. What is the B matrix? This is A. What is the B matrix? What is the B matrix? It's going to be either 1, okay, you can take it 1, and the C matrix equal to B naught. So what I'm trying to say, if you have one input, I'm decomposing my system into single input, the overall system will look like, okay, the P's are the poles are going to be along the diagonal. This is going to have 1, and this is the C matrix. So this is another representation. Okay, in here I think Abdurrahman, you can appreciate this representation.
Of course.
Okay, because this is diagonal. Now also look, this system also controllable and observable as well. Because look, each control is entering the state. So all the states are controlled by the system. So this is another way of, this is another method of finding a state space representation, where in here, okay, let's take an example. Suppose I have this system. Okay, y of s over u of s equal s plus 3, s squared plus 3s plus 2. This is strictly proper, so the D matrix will be zero. The D matrix will be 0. And now I want to do it in this format, in the new format. So let me write this one as C1 over. This is okay. It's going to be S plus 1, S plus 2. Sorry, S plus 3. Now write it as C1 S plus 1 plus C2 S plus 2. The simple pole. Put them in factorized form. And this is basically what we have. So now what is my system? What is the state space representation then? First of all, what is the system order?
Second order.
Second order.
So the A matrix will be what?
-1, -2.
-1, -2, 0, and
Zeros.
along the diagonal only.
x1, x2.
x2 plus
Plus 1,
1, 1, u, y equal to, okay, 2
Yes,
and 1.
that's it.
And this is the representation. So this is their equivalent representation for the system.
Yes. Doctor,
تفضل.
if we have the public info, if we have, for example, in one of the denominator is square plus 4.
Okay.
So we'll have two poles actually.
You will have the complex conjugate. What you are saying, wait, let's say s plus 3 over, after the factorization, you are saying s.
Yes, after factorization, because it will be irreducible.
Okay. So s squared plus, basically, what you are going to have, what do you get? You'll get, this is going to give you what? S minus j, s plus j, isn't it?
And then so you will factorize
okay,
it in
look,
complex.
Look, after, yes. What you'll get them complex, okay, but you have to, okay, after, well, in this case, look, in this case, you have to combine them. Okay, after, okay, get each one. Okay, usually, okay, you don't want the A matrix to be complex.
Exactly.
You don't want the, yes, you don't want the A matrix to be complex. Okay, so in this case, the representation, okay, well, first of all, the diagonal, so the diagonal,
Because you know, for the premise that we can factorize
yeah,
the transfer function is not always the case.
Yeah, look, you can factorize, you can, what I'm trying to say, write it as, let's say, C over S squared plus 1 plus, let's say, A, what you are saying in here, okay, let me, 1 over S squared plus 1 plus, let's say, that's what you are saying.
Yeah, but what are the poles now?
The pole, yes. You are talking about this one.
Exactly. And this is, Doctor, the issue, because in sophisticated system.
Wait. Look, you are always going to the extreme. Now, well, look at it. Okay, so take 1 over s squared plus 1 times u equal to, let's say, y2 or y1. Okay, and do this. I don't remember it directly. Now, take this is going to be y double dot plus y1 double dot equal to u. Do you agree? Okay.
Yes.
Now, أعتقد يطلع بال they call it Jordan canonical form. Look, what we are going to get in here. So let x1 equal to y1, x2 equal to y1 dot. Okay, so x1 dot equal to x2 and x2 dot equal to what? It's going to be equal to minus x1 plus u. So what is the A matrix in here? It's going to be 0, 1, okay, minus 1, 0. Okay, this is x1, x2 plus 0, 1 u. This is the representation for this part. Okay, you can put it disjoint with the other part.
So the idea here, I have to disjoint.
Yes.
The two matrices.
Yes. Because you don't want, okay, you don't want your A matrix to have a complex number. Okay, you don't want to have a complex number.
But at the end of the day, if we calculate the eigenvalues, we will get the complex, right, Doctor?
Yeah, the eigenvalue complex, yes. But
of course.
But the eigenvalue complex, but the polynomial, it doesn't. It's not. I mean,
I see.
Coefficient of the polynomial of the transfer function is going to be always real.
Yes.
Okay, Shabab, we we'll stopping here. If there is any question, I will be more than happy to.
Thank you, Doctor. This is really a good point about S square plus 1, because this is
look, as I said, there are many methods. There are many methods of approaching this, but one of them is, as I said, this is the one of we are describing just simply three